So, and we have been looking at the following. So the title was chapter 5. So we assume that we have some first order configuration diminishing TVD method, like the upwind method or Friedrichs or Rusanov. And then we want to extend that to higher order by using the muscle approach. And the idea is that we have our domain, our unknown, and we have a couple of cells where we have our midpoints, and we focus on the cell J with the boundaries xj minus 1/2 and xj plus 1/2. And these boundaries we call also faces of the control volume. Then we have here the xj plus 1 and the xj plus 2 and the xj minus 2. We assume there's some distribution for the values, which was something like this. We had, and then we have been trying to get a more accurate representation. And lastly, we were discussing how we can, instead of having a constant distribution we call reconstruction in the cell, to have a linear distribution or a linear reconstruction. And then we argued we could take the slope that is coming from the left, or we could take the slope, then we would have this. So this would be then the slope, or we could try taking the value on the right, and by that get then a distribution would look like that. So we have to make our choice. And it turns out, as we discussed last time, in this case, when the slopes have different sign, it is then indicating that we are at an extremum, near an extremum. And in this situation, we don't take either of them, but we take the slope 0. That is the slope that we would also have with the first order method. So then we assume that we have this distribution here. So the value that we have here, so we don't take these, neither of them, because they have different sign. And so this is then the value uj, that will be then the left value at the face j plus 1/2. So then we will use this value here, that we have here, so it will be then the, let's see, it will be then the uj plus 1/2 from the left. That is the one that we used there. When we would go here to this face, we would use then for this face, this value here as the right value when we compute the flux here. But let us focus on this one. And then we argued when we have the slope this one, and we compare them. I take this a little bit down here to see. Here we have. So the slope, this slope that we have here, is smaller in absolute value than this one. And then we take the slope that is closest to 0, so the smallest in absolute value. So that means in this case, we shall take the distribution not from this slope here, but we shall take it from this slope. So we take then this one. So that will be then the distribution, determined by the values here. That is this difference essentially divided by the delta x gives us the slope. And that choice that we have done in this way, and then the value that we use then to evaluate the flux is then this value here. So this value here will be then the uj plus 1/2 from the right. In the first order method, we would take the uj and we would take this is the uj plus 1, the value here. We would take that. So this is the uj plus 1. But when we do the muscle approach, we use these extrapolated values because they give more accurate values at the boundaries to compute the flux. So then we want now to have a formula for that. And they are the following. So call it the extrapolated values. In fact, we are using also information from the neighbors. So extrapolated in the sense that we go from this value here and from this value here. But we are using values that essentially give us an interpolation in a sense. But I call it, let's call it extrapolated. The extrapolated conservative variables that we get with the, it's called slope limited. Because our slope is then not the one that we take straightforward, but we limit it in the sense as we just discussed. Muscle approach. And the following. So we have the value that we extrapolate from the left at the phase j plus 1/2 by taking the value in the cell j that we are working with. So that is the value here. And then we add half of the difference that we would have, say, at uj minus uj minus 1, or taken from that, but limited. And we express the limiting by a function that we call min mod. We define that shortly. And that checks exactly what we did also just in the sketch. That checks the difference to the left, uj minus 1, and to the right, which is uj plus 1 minus uj. And then it takes the smallest in absolute value. If they have the same sign, if they have different sign, it takes 0. And then the one from the right, uj plus 1/2, extrapolated from the right, that is then starting from the value uj plus 1. And that will then take minus 1/2 times the difference that we get, or I could say also 1/2 delta x divided by the, multiplied with the slope. But the slope is just the difference divided by delta x, therefore we can cancel the delta x like we did here. So what we get is then the uj plus 1 minus 1/2. And now we check the slopes that are relevant for the cell j plus 1. And that is uj plus 1 minus uj, and this is uj plus 2 minus uj plus 1. So uj plus 1 minus uj, and uj plus 2 minus uj plus 1. So that's all. And this min mod then, that is the min mod limiter. Min mod limiter is defined by what we shall do now. Is the following. And that is just a function in the new exercise. We want to give you just the anonymous function in MATLAB that you can just put in your function that you use. So the min mod is then defined as a function of two variables. In our case, it's the difference, the differences. But also if we divide by delta x, it would be the slope. So we define it in terms of variables a and b. So the a and b are now representing, if we take this here, this is the slope to the left, the slope to the right. And the definition is that we take the value a, the first one, if that has smaller absolute value than b or equal, and we also need that the product a, b is greater than 0. And that means that the slopes have the same sign. If this is positive, that's one option, or if both are negative, that's also possible. But in any case, it would take then a if that has then smaller absolute value and the same sign as b. However, if b has larger modulus, if b is the other way around, if a has larger modulus than b, and if they have the same sign, then that will be taken. So this assures when they have the same sign, checked by a times b, positive, then the one is taken that has the smallest absolute value. So that is a conservative choice where we are by the smallest slope closest to the slope 0. We can take other choices, but this is the, say, the most conservative and most robust. And then we take 0 if the slope is 0 or negative. That is, if one of them is 0 or if they have different sign. And that is, in our case, was the, we had this situation in cell J. In cell J plus 1, we had the situation that this one, the left slope, was the smallest one in absolute value. So, if we do that, then we just need to use these extrapolated values and put them into our flux function and evaluate the flux with that. So that's all. So we had that, we had seen that before. Just one remark on this here. We can avoid the if here. That is also an interesting thing, that we can write this also without the if. That is useful for MATLAB. Doesn't like if so much, like any other programming language. We can do it in the following way. We take the sine of a, that is actually the same that's a MATLAB function, and then we take the maximum of, in MATLAB we have parentheses, 0, then we take here the minimum of the absolute value of a and the sine of a times b. So then the minimum of those is taken, and then the maximum of 0, and this guy is taken, so it's like that. So in that sense, you can just, and that is the one that we are going to give you in exercise 9. But you can just do it yourself. The thing that you should always try to do is to make the functions, also this anonymous function, such that it can take vector values, so that a and b can be vectors, so that you do that for all just as a vector operation, which is then much faster than if you do that inside a for loop. So once we have then the UL and the U right, then we go into our flux function and evaluate that with those values. So then numerical flux is evaluated by, and that we had before, so therefore as the previous number, the fj plus 1/2, that is our flux function of the first order TVD method, and that is a function of two variables. Usually we take here uj and uj plus 1, the one constant on both sides assumed, but now we take the values that are extrapolated, so the uj plus 1/2 from the left, and the uj plus 1/2 from the right. And then we do that also again, as I mentioned also last time, when we compute the fluxes, say, beforehand. So we compute all fluxes that we need, and then when we use that then in the conservation form, we have it available, and we do not need to evaluate the fluxes twice that we would have to do otherwise. Because the fluxes that goes out on the right is entering the cell on the right as left flux. So if you have calculated that once, it is just a different sign, but the values are the same. So that's the idea. Okay, so then let's see how that looks for the inviscid Burgers equation. So here it is abstract, and but we make it concrete now by looking at the inviscid Burgers equation. So that is our example. We consider the numerical flux function for the higher order upwind method. So we take then the flux function that we have been discussing now. Actually, it's a higher order TVD. Well, it's TVD that we go, but it keeps the TVD property. That's the interesting thing. So, and we take then the one that we have been discussing, and actually it is even more general. It is not only for the inviscid Burgers equation I have formulated here in the beginning, just in a more general way for any conservation law. But we can then just in a minute see the application to the inviscid Burgers equation. So what we do here is that we take our flux function, and everywhere where we had before the uj, we take now the uj plus 1/2 left, the left extrapolated type. That means we evaluate the flux function in our conservation law, capital F, with not uj, but with uj plus 1/2 left. And then instead of taking the flux function at uj plus 1, we take it at uj plus 1/2 right. So that is the average of the flux functions. And then we take the characteristic speed that is evaluated in this special way for the upwind method, and we define that shortly, and then we multiply that by the difference. And the difference is now not uj plus 1 minus uj, but the extrapolated ones, the uj plus 1/2 right minus the uj plus 1/2 left. So that is then our flux function. So you see, it is just the same as what we had for the upwind method that we discussed all the time before. The only difference is that instead of uj, we have now the extrapolated value from the left. Instead of uj plus 1, we have the extrapolated value from the right. That's all. And also when we evaluate the characteristic speed, we use these new values. So we are very consequent. So once you have a function for your flux, your numerical flux, you just feed it, instead of with uj and uj plus 1, with the extrapolated value on the left and the right. That's all. That makes this method attractive because from a programming point of view, it is just giving new arguments to the numerical flux function. That's all. So but let us look at the characteristic speed. That is the aj plus 1/2. Is the following. It is defined by the ratio of the flux difference, and that is now uj plus 1/2 right, minus f of uj plus 1/2 left. So divided by the difference in the conserved variables, which is then uj plus 1/2 right minus uj plus 1/2 left. And that we can only do, of course, if the extrapolated values are different. Otherwise we would have a divide by 0. So that is uj plus 1/2 left, and that is not equal to uj plus 1/2 right. And in the case when they are equal, we simply take the characteristic speed that we can evaluate for the flux function, which is then the df of uj. And there it doesn't matter if we take left or right, because if they are the same, these characteristic speeds for uj plus 1/2 left and right would be the same. So that is then the definition of the characteristic speed that is special to the uplift method. And you see again, we are really completely consequent. Everywhere where we had before uj plus 1, we have now the right extrapolated value, uj plus 1/2 right. And everywhere where we had uj, we have now uj plus 1/2 left extrapolated value. And now, what I mentioned in the beginning, for the implicit Burgers equation, we would then have that the aj plus 1/2 is much simpler, and that is because the flux turns out to be like that. What we get there is simply the average of the characteristic speeds that we have. In our case, that is then at uj plus 1/2 left plus uj plus 1/2 right. So all this we can just code in this. So that's enough. That's all what we need. And our flux function then, that is clear for the implicit Burgers equation. Our flux function is f of u, which is u squared half. So then we have everything to evaluate the numerical flux here. So this is then ul plus 1/2 squared half plus this is uj plus 1/2 right squared half minus, we have this average over there, times the difference. That's all. So then you have the numerical flux for the second order TVD method, but it is not second order everywhere. It gets first order near extrema, because near extrema we make the extrapolated values going back to the first order method. So therefore it says higher order, but it is not completely second order. When you do the analysis, depending on the problem, it is say between 1 and 2 for smooth problems. So I think I have in mind something like 1.6 for some nice problems where you have an extremum. If you would not have an extremum, you could get it second order, but usually we have some extremum. And when you have discontinuities, you cannot get it to some reasonable order because of the discontinuity. Discontinuity destroys the order, because the order is only done for smooth functions. Anyway, you get something out of it. So we can see an example for that. Let's see. And you have also the choice in taking another limiter than the one that we have, but the one that we use here, the min-mod, is usually the one that is robust and that usually does the job. Others might be more accurate, but they have a tendency to be not as robust. So let's see. So this is the function that Radar showed you on Tuesday. And the equation here is now the traffic flow equation. And you are going to use that in exercise 9. So this is now computed with the first order upwind method. So that went a little fast. But we shall look later on to all of them. So, but what we can already see from this, there is a problem with this method. And the method has a kink here. You see it? So this is with the first order upwind method. Here's a kink. And that has to do something with the that the method does not recognize an expansion. It doesn't give you a rarefaction wave, but it tries to give you an expansion shock. So it's a little sign of that. You can make it better when you fix that. But here it is without any fix. So then we look now at the muscle. So that looks very similar, but it does not have this problem with the kink. So there's nothing, you cannot see anything. If we do the comparison 1-to-1, for this case, you see the initial condition in green, and the first order is the blue with the circles, and with the crosses, the red one, that is the muscle. So we see it is going quite smoothly, and also the shock is resolved similar well as with the upwind method, which does a good job here, because we chose the C max as 1. So we have essentially only 1 point in the shock. Here's a little kink there with the muscle scheme, but not so serious. So in general, we get an improvement. We get more accurate results. So this is typical for that. Another example, let's see, is to go to another point here. Let's see. That is actually now from gas dynamics. We can apply all the ideas that we have here to more complex hyperbolic conservation laws and even systems. And here I applied it to in the discretization of the Euler equations. And let's see, so that is the problem I mentioned in the beginning when we started with this chapter on the Burgers equation, when we have this shock tube problem. So we have, and here we look at the density. So here is our diaphragm at time equals 0. So we have, it's non-dimensionalized with the density on the right, which is 8 times higher than on the left, 8 times higher than on the right. And then we let the thing go and see what is happening. Here a shock is developing, here is a rarefaction wave, and this is an expansion fan corresponding to our rarefaction wave. So that is the result that we observe here. That is the numerical simulation of that. Let's see. Well, here we have an example of a comparison, which shows the distribution of the Mach number in this case. Here we have x, here we have the original position of the diaphragm, and here we have the Mach number. So what we see here is the shock. So that is resolved fairly well, and we have a comparison here using the Ruzanov method. which is a little easier than the upwind method, in particularly for the Euler equations. So that is the blue curve, dashed curve, and the solid green, that is then with a muscle. And there you see also the TVD, so it's the second order TVD, but we also use a higher order method in time that we shall see in a minute. So here at the shock we don't see much difference, but at the contact discontinuity, there's we see a big difference. So using the same grid size but using muscle gives a considerable improvement of the resolution of the contact discontinuity. That is the discontinuity which is the difference between the fluids. If we had helium on the left and air on the right, that would be then dislocation. Left helium, right gas, and air in that case. So we get more accurate results with the muscle here. And also the expansion fan or reflection wave that is resolved better with the muscle approach. So without doing too much, just doing what we have discussed here, we can improve the methods. However, with this approach, you need more, say a more accurate, not more accurate, but a time discretization that has a larger stability domain. The Euler, the explicit Euler, is not good enough. And therefore, that is then the topic that we shall discuss shortly now. Okay, so that is then motivation why it pays off to take the effort of doing this muscle approach. And it is, as you see here from these extrapolate from these examples, it is not really much of a difference. It is just exchanging the variables that we otherwise use by extrapolated ones. So now we have the motivation to study also a higher order, not also it's a higher order, but say a more stable time discretization, a time discretization with a larger stability domain. So that is the thing that we want to do next. Let's see. The method that we are going to see is the one that I used here. It is called third order TVD Ramme-Cutter method. But to get started, you can use this muscle approach even with the explicit Euler method. You don't have a too fine grid, if you don't compute too long, then it will be for the short time, and for coarse grids it will be okay. But as soon as you go over longer time or you have finer grid, you will see an instability. So therefore we should use then a method, time discretization, that has a larger stability domain. Okay, so that is then getting us now into time discretization. TVD Ramme-Cutter method. So that method was developed in 1998 by Gottlieb and Schuh at Brown University. And later on they called it also strong stability preserving. Strong stability preserving. Or SSP. So when you see then SSP method, then it is this. And that is then needed for higher order TVD methods. You can use also other methods, but this has the property that it keeps the TVD property in time. Okay, the acronym TVD, total variation diminished. So let us start from the very beginning. We do a spatial discretization, that is what we have been discussing so far in great detail. Using methods in conservation form, and which are TVD even, and we have been discussing discretization of conservation laws of the following form: ut plus f of ux equal to 0. And we have seen that if we do that only the space discretization, that will lead, using the method of lines, where we only do space discretization, to an initial value problem for ordinary differential equations, which we also call semi-discrete equations. So that leads to the semi-discrete equation. That looks like that. That we have a time derivative of u, and u is now our vector containing all our unknowns. And on the right hand side we have our what we call the residual. Here we have now the u is now the vector with our unknowns. Say we have u1, u and j. That is, these are our unknowns at the grid points 1 to nj. And the r, that is the residual vector containing also nj components, and that is then the following. So if we look for the component j of the residual vector, it would look like that. We would have rj would then be a function of the vector u, usually just the nearest neighbors. We write it in this form. And it would then have the form that we get from the conservation form, that we have our flux function fj plus 1/2. Now, for simplicity, we discuss it for the first order method. You would then have here the uj and the uj plus 1. For the muscle, you would have here the extrapolated values, minus the flux at j minus 1/2. That has the arguments uj minus 1 and uj divided by delta x. So that would be then our residual. That would be the residual of a first order TVD method. If we want also to see what it would be for the muscle, we just can do that. And say the rj of u for the muscle would then be minus, and then as already mentioned, we would have here the extrapolated values. The uj plus 1/2 left, the uj plus 1/2 right, and for the flux j minus 1/2, we would have the same thing at the face j minus 1/2. So the uj minus 1/2 left and the uj minus 1/2 right, divided by delta x. So that would be the residual of the higher order TVD method. That is, as we mentioned before, somewhere between first and second order. So when we have a problem that doesn't have extrema, it will be second order, otherwise it would be first order at extrema in any case. So, and that will be solved then now this semi-discrete equation will now be solved then by the third order TVD Runner-Kutta method. So 56, that is the semi-discrete equation is solved, or it can be solved, you have other choices of course, by the third order TVD, it is in the title, Runner-Kutta method. And that is, as mentioned before, due to Sigal Gottlieb and Jiwon Shu from Brown. And that looks the following. Let's take that before we break. So it's just 3 lines. And if you do it in a clever way, that is, if you define this residual as a function, in our case it would be a MATLAB function, then you get only 3 lines of code for getting this then also in your MATLAB code. So, and this is the following. In Runner-Kutta methods we talk about stages. So in that case we have 3 stages. To get from time level n to n+1, we do it in 3 stages. First stage, u1, we get by the value at the old time level. That is now our vector u at the old time level. And then we add delta t times the residual evaluated with u at the old time level. If you look at that, that's just an explicit Euler step, nothing more. That you, if you have done that already for explicit Euler, you have that already. Second stage is called U2. That is, let me give it brackets here to not confuse it with the time step. So that is, I took here a bracket instead. In the second stage, we do a certain average of the value at the old time level and the value that we have just computed in U1. So this is then some average. And also we take some fraction of the residual evaluated with what we have just computed. And here you see already what I said. If you have a function for r, then you call it here with the old time level, and here you call it with the value after the first stage. Same function. And then the third stage, you get the solution at the new time level already by taking again a certain average of the value at the old time level, and in that case of the solution after the second stage, so we get second stage value, and again some fraction of the residual evaluated with the second stage value. Again, using the same function r. So that's it. So when you have the r as a residual, this is 3 lines of MATLAB code. And it has then the advantage that you do it as vector operations. So of course your r then should be such that you have then, well, you can take the advantage then inside the r that you do that also as vector operations there. So then, and this is the good thing, this method preserves the TVD property in time. Call it the RK, or I call it RK3. That is the method 57. It preserves the TVD property in time. Okay, let's stop here. Take a 15 minutes break.